Thank you for joining us for the guest speaker series. At this time, I'd like to introduce Red Jensen. He is a subscale engineer and UAV pilot for NASA's Armstrong Flight Research Center. He's got the best job in the world. He is involved in all the subscale aircraft designs and flying at the model shop there. So welcome, Red Jensen.
Good afternoon. Thanks, guys, for coming. They are correct. I do have a great job. I love it. I feel very lucky every day. My name is Red Jensen, and I run the Subscale Flight Research Lab at NASA Armstrong. A lot of people may not realize, but NASA has a long tradition and history with using subscale radio-controlled aircraft for flight test. The lab that I'm in now has been in operation in various forms since the early 1950s. A guy named DROID, a gentleman here in the black and white photo, is who it's named after. He's the father of the lifting body. You can see him holding a stick and tissue model of the M2F1, which was the first successful flying lifting body there, standing in front of the real lifting body behind him. And he was a model airplane guy. He was an engineer at NASA. But for fun, nights, weekends, he went home and built model airplanes. He had one of the very early radio control sets in the Antelope Valley. And he was the first guy to successfully fly and land a lifting body. The lifting body program came into being because he was showing home movies of his experiments for fun at home. Made the rounds. Eventually the center director, Paul Bickle, at the time saw it and started socializing it. Milt Thompson, who was a very famous test pilot, sort of adopted the concept and said, yeah, I'll fly it. I think that will work. And the whole idea is to return from space gracefully like an airplane and not underneath a parachute in a capsule. The reason for that is many. One, pilots don't have egos at all. So they love coming down underneath the parachute, no control. That's not true. They want to fly, right? They're pilots, so they want to fly back. They want to choose where they're going to land. In reality, though, splashing down in the ocean at the whim of the wind and hope to be picked up by the Navy is problematic. When you can fly back, you can choose your landing area. If you have a weather issue or you have some other problem where you can't go to your intended landing site, you can divert and you can fly somewhere else and you can land. Same reason the space shuttle used to land at Edwards and also in Florida for weather, things like that. So Milt Thompson was a huge advocate of it. Milt was also an X-15 pilot, very well respected. So his word sort of helped propel it along with Paul Bickle. And they built the first lifting body. That vehicle that he's standing in front of is still at Edwards Air Force Base today. You can see it if you can get on base. It's at the Air Force Flight Test Museum. It will be moved outside the gate eventually so that the regular public can come see it. But for now, unfortunately, it's behind locked doors. But it's cool. It was built in El Mirage by the Brigley brothers. The outside shell was built by some sailplane guys, and the inner tube structure was built at Dryden. And then they were married together, and they eventually towed it with a Pontiac car across the lake bed. The photo on the first slide there is in an airborne towed flight, towed behind a DC-3. That came later. They made some 93 car lake bed towed flights before they tried to fly it behind the DC-3. That first photo there is kind of interesting to me in that it shows where we've been, no wings, and where we're going, all wing. Sort of backwards. You'd think back in the old days you're working with wings and then now we're using it without, but it's the other way around. So models have played a part in almost every major breakthrough along Dryden and now Armstrong's history. Subscale flight is cheaper, it's usually quicker, and it's much less risky because there's nobody on board. You can test something with a model very quickly and find out whether it's worthwhile or not before you commit it to a manned program. So oftentimes we can get data in weeks or months where it's years or tens of years before you get data out of a full-size program. Now obviously we can't go as fast as the manned stuff goes, or we can't go as high, but we can do a lot of things that they can do much quicker. The lab itself comprises of some 25 aircraft in various states of duress, I should say. At any one time we have about a dozen that are flyable and then some that are being worked on or built up or torn down or reconfigured or something like that. So we're very busy. There's 3 of us full-time in the lab. Myself, I'm a lifelong modeler. I grew up in the garage with my dad building model airplanes, some of my fondest memories. I soloed when I was 6 years old on a plane called a Mini Mambo. And ironically, Hap and Nancy Miller, who run Miller RC, they have a booth down the way here. Hap was there the day that I soloed, almost 40 years ago. So pretty neat that that's kind of come full circle. I've been an airplane nut. I love anything that flies. I learned how to do composites along the way and structures and all that other kind of stuff. I worked for a UAV company prior to coming here to NASA. And along the way, I've got somewhere around 25,000 hours of unmanned time. I'm also a private pilot, although that's really expensive, so I don't do that as much as I like. But I like mainly fast stuff, but I'll do it all. Those two bottom photos there are from my previous life, flying aircraft, protecting the nation's forces around the world. Derek Abramson is our other full-time guy. He's an electrical engineer. He's mainly responsible for all of our integration and wiring of the electrical components. He's got a master's degree from Long Beach, and all-around great guy. Also, lifelong modeler, right? Grew up building model airplanes and doing stuff like that. His previous life, he was in the Navy, worked on CV-22, and brought a lot of that sort of experience and dedication to what we do in the model lab. Third guy is Justin Hall. We hired him specifically to be a pilot. He's a local guy to where I live now, Palmdale, Lancaster area. Again, lifelong modeler and all-around great pilot. We were short on pilot capability, so we brought him on, and he's quickly filled the role and doing a great job at that. Fits right in with the rest of us nut jobs. So again, early on, models were recognized as providing value in flight research. Dale Reed, the gentleman there in the in the yellow shirt on the left, you can see him holding a parafoil with the M2F2. And the idea was, early on, they recognized that these lifting bodies, while they flew, and they flew well and were controllable, they had a lift-to-drag ratio of a brick, somewhere around 3 or 4 to 1. So very, very steep glide. And again, the emphasis was on extending the cross-range capability. How far can we go from our initial entry point? Where else can we go to potentially land, not straight down? So they toyed with a bunch of different ideas. This particular one happened to be a parafoil. So once you descend through the atmosphere, get subsonic, the parafoil is deployed, and then you can sort of glide back. Problem with a parafoil is you're at the mercy of upper atmosphere winds. Sometimes you can have 60, 80 knots of wind, and well, you're not going to penetrate very far like that. So that was scrapped early on. Not really scrapped, but decided that it wasn't going to work very well. Later, Dale was also interested in these deep stall recoveries. And was anybody here yesterday and listened to the Spaceship One talk? Well, the Spaceship One takes off vertically or launches horizontally, climbs vertically, passes the von Karman line somewhere around 325,000 feet, and then when it descends back through the atmosphere, it pops the tail up, and they call it a feather. All the modelers call it a dethermalizer. Anybody fly free flight? Same sort of idea. It naturally puts the aircraft at a positive angle of attack, high drag configuration, and is very controllable and stabilizes on its own. Well, Dale Reed was doing stuff like that back in the 70s and 80s with a full-scale sailplane. This is a Schweitzer 136. And you can see the tail popped up there, and it would enter a deep stall, so the whole aircraft would be stalled and descending vertically, yet you could still point it where you wanted to go. So once the aircraft would decelerate, the tail would come back down, and it would fly away. And that's Dale kneeling down there on the left again, and right next to a model 136. Anybody spot the make of transmitter sitting up front there? Yeah, it's an old Craft. We still have it, actually. We are the first A in NASA, so National Aeronautics and Space Administration. So we don't do a lot of space stuff, but we concentrate on the aeronautics side, but sometimes that crosses over. This is an aircraft called the Mini Sniffer, and this is actually a series of aircraft and a whole series of attempts to fly or potentially fly a fixed-wing aircraft on Mars. So Mars has a very, very thin atmosphere. It's not air. You'll notice at the back of this aircraft there's a motor, and the engineers thought that they could use an internal combustion engine to fly on Mars. Well, there's no air there. How are you going to combust? Well, the answer was they used hydrazine, compressed hydrazine, and ran the engine with that. And while it worked, it was problematic. The hydrazine would wash down the cylinders, scrape all the oil off, the bearings would fail, the rings would fail. So very, very short lifespan on the engines. So while they proved that something like this could fly in a very thin atmosphere, and potentially be powered, it just really wasn't feasible. So this aircraft's called a Space Wedge, and we have this. It's actually sitting in our booth there if you'd like to see it. And the idea is it's a lifting body shape, much like the traditional lifting bodies that you've seen. However, once it was, again, through the atmosphere, deploy another parafoil. So this is sort of a follow-on to the earlier series. They hadn't quite figured out that it wasn't the right way to go yet, so they kept trying it. And initially, it was hand-launched off of a slope with the parafoil deployed, much like a slope glider, into Tehachapi. Later on, you see the two engineers there working on it. That's Jim Murray on the left, he still works there to this day. One of the greatest guys at NASA. I really like him. They were throwing it out of Cessna 206. They'd literally open the door, chuck the thing out, and it would tumble and then pop the parafoil and fly home. And then later on, it was flown and dropped from a RANS S-12. That bottom picture is an ultralight. So that's a manned ultralight that was converted to a UAV. Had giant servos in it and a pretty typical RC type system. And I believe it only completed 2 drops from the Better Duck, which is what that aircraft was called. So a UAV dropping a UAV of a scaled reentry vehicle is what that was. So continuing on with that theme, they decided that a more airplane-like shape would probably do better once that you had decelerated and entered the atmosphere. So these tests of the I-2000, which is this aircraft right here, was an inflatable wing. So wings are problematic when you re-enter. They're long, skinny things that have sharp edges, and when you re-enter the atmosphere, those tend to burn off, and that's why you see sort of a commonality in the shapes of the lifting bodies, Spaceship Two, the Space Wedge, all that sort of thing. You want to present sort of a blunt surface to the oncoming atmosphere, and that's what heats up and you decelerate, and then it can sort of fly like an airplane after that. So again, the idea here is to not necessarily define a new shape of the vehicle, but will an inflatable wing work to extend the cross-range capability? Can we get a lift-to-drag ratio maybe as high as 8-to-1 instead of 4-to-1, double it? So this was dropped from our mothership, which is a big RC airplane. And you can see in that sequence there that the wings deployed. 300 psi of nitrogen were pumped into these wings. And this is an interesting bit of technology here. I'm sort of fascinated by it. The outer skin is like a spacesuit material. It's ripstop nylon. The inner is a very soft foam padding like you'd find in a couch. And then these chambers have a Kevlar sleeve on the outside, and then the inside is just a Lexan tube. So you would inflate these chambers, and that would be stiff enough to act as a spar. So if you guys want to toss that around, Mason, check it out. So incredibly low-tech solution to a high-tech problem, and it's elegant in how they figured that out. So that's pretty interesting to me. These two aircraft that are sitting here are on loan back to us from the AMA Museum. They normally are in Muncie at the Model Aircraft Museum, and they were gracious enough to crate them up and send them back so that you all could see them. Pretty cool stuff. Here's a video of the I-2000 flying. So you can see the wing deploy happens very, very quickly. And it's a 3-channel model, uses rudder, elevator, and then differential elevator to act as ailerons, so no flight control surfaces on the wing itself. You can see it flies quite nicely. Not exactly a trainer, but controllable. It works. So continuing on with that theme, we took the X-24 shape, which is a traditional lifting body, and added, again, these inflatable wings. That wing that's being passed around is from this particular aircraft. This aircraft is also here. It looks a little bit different. It's different colors. It's been rebuilt after a mishap, but it's the same aircraft. So same sort of thing. It was taken up by the mothership, dropped, and you can see follow the sequence there. You can see here they had an isometric deployment, though. The right wing popped out, and the left wing is still folded in that 4th or 5th shot there. Caused a little bit of a roll-off, and I believe it was on this flight that it hit the ground. Is that right, Jerry? Do you remember? So it hit the ground, underwent a rebuild, and then it was flown a couple more times, but after that it was shelved. This particular airplane is pretty fascinating. You look at it now, and it's not too different from a giant indoor model or something rubber powered. But you have to remember that this was built 15 years ago, and it's running a little West Technic geared motor in the front. It puts out 8 watts of power, a whopping 8 watts. And this particular aircraft is powered by a ground-based laser or searchlight. So the idea is alternative energy. How can we fly things longer with a ground-based power source? So a searchlight was pointed at the solar cell, and that's what actually powered the aircraft. There is no energy storage on board. There's no batteries at all. There's no speed control, in fact. The solar cell is plugged directly into the motor, and it is also plugged directly into the radio control system. So until the spotlight is on the aircraft, it didn't work. So they would launch it, shine the spotlight at it, and fly around for however long you want, and then to turn it off, you simply move the spotlight away, and it would free flight down to the ground and land. So the ultra simple, ultra lightweight, and it's what we call a technology demonstrator. It was designed to simply prove that it could be done. And it did it well. The airplane weighs 8 ounces, and it's flying on around 14 watts per pound. So typical trainer aircraft that you might fly as an RC model are about 50 to 75 watts per pound. So the power loading is incredibly low. 1 kilowatt light shining at it, incredibly inefficient, but it works. And so we'll show you a video of that next here. And if you notice, if you watch the video, there's going to be a red dot in the middle of the solar panel, and that's how they actually aimed the laser at the aircraft. So if you keep an eye on it there, you'll be able to see the red dot if you're eagle-eyed enough. So this is an earlier flight, end up going to a larger solar panel. And it was really simple. The guy just simply walked around with the light, pointing it at it while Tony flew the aircraft. You can see the red dot laser there, trying to keep it powered. So very simple, just comes in and lands on the solar sail. That program kind of never really went anywhere either. The idea was that we could maybe power a satellite in space or a high-altitude blimp or some high-flying aircraft with a power source from the ground. We figured out all the wrong ways to do it. Sometimes we find the right way. Now we're going to talk a little bit about the current projects and some of the stuff that's currently going on within the lab there. You see Twin Glider. We'll talk about that a little bit more later, but right now we have about 7 projects going at any one time, and some of them use the same aircraft, some of them use different aircraft, and some of them have their own completely unique set of aircraft all to themselves, and some use a mixture. This particular project here is pretty interesting. The aircraft is nothing special. It's called an APV. It's built by R&R Composites in Northern California. It's just a flying truck, nothing really special there. What's special about it is it's got a fiber optic strain sensing network embedded into the wings. And what fiber optics do, and the strain sensing network does, is it measures real time how much the wing is deflecting and deforming in flight. And we take that feedback, and if you look real close at those 2 black wings, the top one is the underside, you can see 22 separate servos and 22 separate control surfaces. And the idea is we can take that data from the wing flexing and counteract that flex with the control surface. So we'll deflect the surface in the opposite direction to relieve the root bending strain. The idea being that if we can design an intelligent structure, that someday we can build wings that don't have to be stressed to 8 Gs. We can build a wing that's stressed to 4 Gs or 3 Gs, and then when it encounters turbulence, you deflect the control surfaces and gain back that extra strength. So if you think about an airliner, airlines are all about money, right? It's how fast can you get from one side of the country to the other, and how efficiently can you do that? Everybody's seen a winglet, right? That's another NASA invention, by the way. Now, winglet gets you 3% fuel efficiency savings, so 3% less fuel to do the same job cross country. If you can not have to drag around a 6G wing, you only have to drag around a 3G wing or a 4G wing, imagine how much weight you save, because you don't have to build a structure that strong. So now you have an intelligent structure that comes back to you guys in cheaper ticket prices, right? So an airliner spends its life at 1G or 1.5G. It spends very brief times exceeding that. Maybe a rough landing, probably not, but more like turbulence. Or you're flying through some rough air. That's when you have to have that extra structure. Otherwise, when everything's going right, it's just like riding on a bus. You don't feel anything. It's very nice. So that's what this research is here, is building a more intelligent aircraft structure. This little video I'm going to show you here, this is Ben Martins. He's been with us 3 summers. He's an intern. He is a high school dropout. He'll be a doctor in less than a year. Incredibly smart kid. This is one of those kids that traditional school didn't work for him, and he had to find a way to apply his intelligence to something that he believed in. So he's going to tell you a little bit about what he's doing here.
So my name is Benjamin Martins, and I'm an Aeronautics Academy intern here at Armstrong Flight Research Center for the summer of 2014. Currently, the major factor in the design of an aircraft is the weight of the aircraft. You have to generate enough lift to overcome the weight. And so if you can reduce the weight, you can reduce the amount of fuel that you're using.
Should say something configured successfully?
So what we're trying to do is we're trying to use the segments on the plane to redistribute the load, and that way we can have less structural weight. The plane will still be just as safe and just as strong, but we can use the segments on the control surfaces to make this structure more intelligent. So right now there's 44 segments on the main wing control surfaces. A traditional wing has 1 flap and 1 aileron per wing, so 2 control surfaces. What we did is we broke those up into segments, and that allows us to reshape the load using localized input or small inputs rather than the whole control surface. So the control algorithm works by activating single segments in an attempt to redistribute the load into a more favorable configuration. And again, that configuration will allow for lighter weight structures in the future. The aileron are the outer control surfaces on the wings, so that's what allows the pilot to bank the aircraft and make a turn. So the major benefit would be fuel savings, which as a consumer would lead directly to costs, so the price of airline tickets would be cheaper. It's also better for the environment.
Yeah, we could do that, Ben. Actually, you can do that right now.
I'm very excited to be part of this project. I came for the summer of 2013 and helped transition the aircraft from a stock aircraft into the segmented trailing edge aircraft that you see behind me. I was very passionate about it. I took parts of it home to finish after the internship had ended, and I was lucky enough to come back this summer and work on it again. I have a great team behind me who's helped this summer developing more advanced control algorithms and better aerodynamic modeling, so we can really predict the behavior and get the maximum results possible.
So that FOSS system is also a NASA invention. We have a couple of really smart people that invented that. The fiber optics themselves are off the shelf, but the computer and the laser and the way that it processes all of the data is unique to us. It's probably worth mentioning that what NASA does is we will patent that. We patent a lot of the things that we do, but we don't patent them so that nobody else can use it. We patent it so everybody else can use it. We patent it so that some major company can't take it and then have an exclusive on it. We want everybody to be able to use it. So everything that we do is for the public. This particular aircraft, X-56, is a similar aircraft to the APV that you just saw, in that it's also doing research into flexible wings and intelligent structures. This also has a fiber optic strain sensing system on board. It's powered by 2 JetCat P400 engines. It weighs about 550 pounds, and ultimately it'll fly at around 180 knots. Our role in this particular aircraft is simply support. We don't actually fly this one. We just offer engineering and integration support. We're hoping that next year we're going to have that aircraft here. It's undergoing some maintenance right now, otherwise we would have brought it. But it's pretty interesting. It's a 25-foot wingspan aircraft, fully hollow monocoque, carbon fiber composite. And it's flown from a ground cockpit by our test pilots. They sit in an actual control room looking at several video screens, and they fly it just like they would fly anything else, except for they're looking through a camera instead of out a window. And they're doing the same sort of thing, flutter suppression and gust load alleviation. This aircraft is DROID. We have 4 of these aircraft. 3 of them are flyable. 1 is kept as a spare. And these are basically our flying dump trucks. They're our test beds. They're not tied to any one particular program, but they help out on a ton of different programs. We have DROID 3 here, which is configured as a tow plane. It's got a larger engine on it. You'll see it later on towing around some gliders. But DROID 2, which is pictured here, was used in a program called Auto GCAS, or Autonomous Ground Collision Avoidance Software. And what that's attempting to do is basically save people's lives. Every year, pilots crash into the ground for no good reason. It's called CFIT, Controlled Flight into Terrain. You have a perfectly good pilot flying a perfectly good airplane, and he hits the ground for no good reason. JFK Jr. was killed from CFIT. He couldn't see. A lot of times it's haze or fog, or the pilot gets disoriented, or there's some reason that the pilot is not paying attention or doesn't have all the information to successfully fly the aircraft. So what the engineers at Dryden did is they took a world terrain database, much like Google Earth, but Google Earth didn't exist then, shrunk it down to fit on an Android-based cell phone, and then put it on board this aircraft with a piece of software that would allow the autopilot from the aircraft to interface with the terrain map. So what that gives you is the ability for the aircraft to know where it's at in space in relation to the ground, because it has a terrain map, but it has an added layer of having all of the autopilot data coming in. So it knows how fast the airplane is flying. It knows what the minimum turn radius of the aircraft is. It knows what the max G load of the aircraft is. It knows all of the performance parameters so that it continuously makes a decision on how to best to avoid the obstacle. So right now you can get an app on your phone that will tell you when you're going to collide with the Earth when you're flying around in your GA airplane. It just tells you terrain warning, pull up, whatever. This is different, and then not only does it constantly recompute the best trajectory to miss that obstacle, but it will also take over control of the aircraft if necessary. So if the pilot becomes incapacitated for some reason, this system will take control, avoid the obstacle, and return the aircraft to straight and level flight. We know of 4 saves now that have happened with this particular system. I've seen video of 2 of them. I'm going to show you video of 1 of them, and I'll talk about the second one a little bit. But it's pretty dramatic to know that this is essentially an off-the-shelf model airplane. It's a Bruce Tharp Flying King. This is a Super Flying King, which is double-sized. It does have some other equipment on board, but it's essentially a model airplane. Model airplane servos, model airplane linkage, model airplane wheels, model airplane motor. It's covered with monocoat. I mean, it's a model airplane. Yet we're able to do this cutting-edge type research with a very low-tech thing. And this perfectly illustrates the reason why we have a model lab. So we're intentionally flying this aircraft at a mountain peak. You can see that bottom right corner. That's Fremont Peak in the background. And the aircraft was within 1 second of impacting that peak. We put a waypoint on the other side of the mountain, told the aircraft to fly through it, and let the system take over. Jerry here in the yellow shirt was one of the pilots on that program. So again, just because it's a model doesn't mean it can't be extremely useful. So let's take a look at this video. I'm going to let this play through once, and then I'm going to go back and we're going to talk a little bit about it. I'm going to point out some things because it's a lot going on all at once. This is a heads-up display or a front view out of a F-16 cockpit. This happened about 6 months ago at Luke Air Force Base, a flight of 4 F-16s on a training flight. And in this particular instance, the pilot G-locked, which is G-induced loss of consciousness. He was pulling enough G, he lost the blood flow to his brain, and he blacked out. So he was unconscious during this. So not everybody's probably familiar with HUD symbology, so we're going to just go ahead and play it, and then I'll rewind it, and I'll kind of point out what everything is.
Two recover. Two recover. Two recover. Two recover. Sully, knock it off. Sully 1, knock it off.
Sully 2, knock it off.
2, get yourself back above the floor. Sully, knock it off. Sully 1, knock it off.
Sully 2, knock it off.
Alright, 2, climb back above 12,000. right. That,
So, right here is the airspeed of the aircraft. Right here is the G load. That's how many G's he's pulling. And then over here is the altitude. So what's going to happen is you're going to watch the G build up. It builds up to a little bit over 8. He will go unconscious, and you'll watch that G load drop to down to 1 G, which is just free flight of the aircraft. At the same time, you'll see the airspeed starting to build here and the altitude to decrease. And then you hear his instructor, Sully, pull up, Sully, pull up. He knows he's unconscious. He's heading straight down, eventually goes supersonic, straight down, and then the system takes over. Now, you can tell the system takes over. These 2 arrows come in from the sides. They're called chevrons, and they come in and they touch. That's called a fly-up, and you'll see it display fly-up in the HUD. When that touches, the pilot is no longer in control. This particular incident, I'll have to double-check, but I'm pretty sure it gets within 5,000 feet of the ground. So at supersonic, 5,000 feet, 2 seconds till he hits the ground. So he's 2 seconds from dying. The aircraft executes a maximum G turn, which in this case an F-16 is a little over 9 Gs, so he blacked out at a little over 8 Gs. And in the recovery, if you watch here, I believe he hits 9.1 Gs to make sure that they miss this 5,000 foot hard deck, and then it brings it back to straight and level. So it's a lot to take in, but just watch those 3 things and it'll give you a little better idea of what's going on here. Okay, so he's doing about 500 knots. Here comes the G's, 6 G's, 7 G's, 8 G's. He's now unconscious. The pilot is no longer able to fly the aircraft. He's down to 1 G. See the altitude descending, speed builds up.
2 recover. 2 recover. 2 recover. 2 recover.
And there's the fly up. So it pulls back straight level. 9.1 G's. Back through the hard deck and climbing.
Sully, knock it off. Sully 1, knock it off.
Sully 2, knock it off.
Now that's the instructor telling everybody to knock it off.
Get yourself back
Stop what
above the
you're
floor.
doing, and everybody recover back above the hard deck. So you can hear him breathing now. He's coming back to consciousness.
Sully, knock it off. Sully 1, knock it off.
Sully 2, knock it off.
So he acknowledges the knock it off.
All right, 2, climb back above
He's conscious now.
12,000.
So he's hitting them back above the hard deck there. So that was an app on an Android phone flown in a model airplane that saved that guy's life. There have been 3 others. A second one that I have seen was another F-16 Air Force guy bombing ISIS in Syria. And he's flying at night. He's on the battlefield. And it's the same thing. We can see the HUD symbology. Unfortunately, I can't show that one to you guys. But there's smoke and flames and explosions going off all on the battlefield, right? And he's trying to target this particular installation so that he can release his weapon. There's ground forces in close contact, and he's trying to help those guys out. Well, being at night, poor weather, smoke on the battlefield, all this kind of stuff, he's having a hard time getting his targeting system to lock up on this target. So he makes 3 passes from in excess of 20,000 feet to try to get this guy, right? And he's not able to do it. So on the 4th pass, he's really concentrating on trying to pull up. And again, he's got a 5,000 foot hard deck, which means he's not supposed to fly below 5,000 feet and certainly not drop a weapon below 5,000 feet. So he rolls in. He's low on gas. He announces that this is going to be his last pass, and he misses. He can't lock it up. What he also misses, though, is he misses the hard deck, and he continues to fly through the hard deck, continuing straight onto the target. So they call that target fixation, and that means that he was so focused on trying to get the bad guy that he missed flying the airplane. The airplane missed the ground by less than 1,000 feet. He would have driven right into the bad guys. He would have got them, but at the expense of his own life and expense of an F-16. So again, pretty neat that we can do that sort of thing. This has been successful enough that now all the Block 60 F-16s, F-22, and F-35 come right off the production floor with this software installed. Comes right from the factory. I believe we're about out of time, unfortunately. Talk a little bit about towed glider here. This is an air launch concept. We're aiming to reduce the cost of payloads into orbit. And traditional vertical launch is very expensive for a lot of reasons. People demand the range safety aspect of it, real estate, having a sterile environment, you're tied into a weather window, all these kinds of things make it very expensive. However, if you can air launch, you don't have to be tied to that typical range that you're at. You can move anywhere in the world to air launch. If you can launch from around 40,000 feet, you can also save up to 30-40% of your fuel cost. You use a ton of fuel just accelerating that mass from 0, 1 inch off the pad. It takes a tremendous amount of fuel and infrastructure to do that. So if you can air launch, you get a tremendous head start on that. We have that model over in the booth too. There's a couple of us putting it together. This is Terra. It's basically a twin-engine airliner type aircraft, and we use that for a variety of research testing as well. It's much like a DROID. It's just a dump truck. And I think I'm going to stop there. I have a few more slides to show you guys, but I think we're running short on time. But how about a few questions? We have some time.
Yeah, we
for
got
some
about
questions.
5 minutes for questions.
I'll play this video while we're answering questions. Anybody? Yes, sir.
Your re-entry vehicle that you showed early, you didn't mention Irv Culver. Irv Culver was a part of that whole process.
That's right. Dale and Irv were like that.
Yes.
Yeah.
Yeah, Irv was a friend of mine, and he taught me a lot of things. So
Yeah, obviously,
quite a genius.
there's too many people to mention or programs, but yeah, Irv was a big part of that, and there's a lot of history. I mean, I could literally talk for 8 hours up here about all the stuff that we've just done in the model lab, but you guys would get bored of that real quick.
I was just going to ask, is there an online resource where we can see like the public domain or the patents you're talking about? And
yeah, if you go to the Armstrong, NASA Armstrong page, there's a link to all that stuff from there. You can see all the public stuff. Yeah.
All right, great. Thank you very much, Red. Red, what do you... Go ahead. Red, what do you call your job on a daily basis?
Oh, best day at work ever. Or another day in paradise. Take your pick.
Thank you very much, Red Jensen, everybody.